we can continue with the next speaker, Dahlia Klein from MIT, who will be talking about magnetism in the ultrathin chromium trihalides. Please go ahead.
1 second. Thank you very much to the organizers for giving me the opportunity to speak. So my name is Dahlia, and I'm a PhD student in Pablo Jarillo Herrera's group at MIT. And I'm really excited to share with you some of our results over the past several years on experimental determination of magnetism in the ultrathin chromium trihalides. So in my talk, I will first give a brief introduction to 2D magnets, and then move on to 2 members of the chromium trihalides family. First, chromium triiodide, in which we achieved detection and control of magnetism, and then move into more recent results on chromium trichloride, in which we were able to connect magnetism and structure, and then conclude with outlook on the field. So as most of you are familiar, van-der-Waals materials consist of these bulk 3D crystals in which there are very strong bonds within each layer, but then only very weak van-der-Waals bonds coupling the adjacent layers. And so this makes it very easy for us experimentalists to use the technique of mechanical exfoliation, using Scotch tape or other adhesives to progressively thin down the bulk crystal until it becomes thinner and thinner, and then we can isolate layers down to the single layer limit, which of course in the case of graphite, you obtain graphene, which is a single atomic layer of carbon atoms, and it was first isolated 16 years ago, and then just a few years later was awarded the Nobel Prize in Physics. So over the past 15 years, there's been quite a lot of progress beyond graphene, and we really now have hundreds, if not thousands, of 2D materials that can be cleavable down to the few layer limit. And not only that, but we've also figured out ways to stack them on top of one another into different van-der-Waals heterostructures. And so there's this nice Lego analogy, though there are also quite a lot more beyond Legos, including twist angle control. So the family of 2D materials has really expanded to include more than just graphene. So we have other semi-metals such as tungsten ditelluride. We have insulators such as hexagonal boron nitride, which is also a very nice capping layer. We have semiconductors such as MOS2 and black phosphorus. We also have superconductors and topological insulators. However, until just a few years ago, one noticeable absence from the family of 2D materials were magnets. So over the past several years, there's been an explosion of research into 2D magnets, and we now have a very rapidly expanding list of different 2D materials that have magnetism persisting down to the few layer limit. So we have a variety of insulators and semiconductors, including the chromium trihalides, such as chromium triiodide and ruthenium chloride. We also have conductors, such as FGT, shown here. And more recently, we also have magnetic topological insulators, such as MBT, in different stoichiometries. And I'd like to emphasize that this is really not a complete list, and it is ever expanding. But in the rest of my talk, I will focus on the chromium trihalides. So the chromium trihalides share a common crystal structure, where there's a chromium 3+ honeycomb structure shown here in the purple spheres. And then each chromium ion is surrounded by a nearly octahedral arrangement of halide ions. And then the monolayers are stacked upon one another in 3-atom thick unicells and separated by a van-der-Waals gap, making them naturally cleavable like graphene and other van-der-Waals materials. These crystals undergo an important stacking phase transition where the arrangement within each layer does not shift dramatically, but there's a very big difference between the stacking of the chromium honeycomb nets in each layer. So here I'm just showing 3 adjacent layers. And at high temperatures, we have this monoclinic C2M stacking. And then as you cool below the structural transition temperature, which is quite a bit higher than the magnetic transition temperatures, we instead adopt this rhombohedral stacking. And for those who are more well-versed in graphene research, this is also known as the ABC stacking of honeycombs. So we can think of the magnetic order as being highly localized on the chromium 3D sites. So in the octahedral crystal field picture with the halide ions on the primary axes, we end up with a splitting of the 3D orbitals into the T2G and EG manifolds. And due to the 3+ oxidation state of chromium ions, we expect to have 3 electrons, which will then arrange themselves in the T2G orbitals. And this is all consistent with the observed saturation moments of about 3 Bohr magnetons per chromosite in the bulk chromium trihalides. So the magnetic ordering itself will actually depend strongly on the halide ion, giving a range of different magnetic orderings in this family. So the chromium iodide and chromium bromide are both bulk out-of-plane ferromagnets. So within each layer, the moments on the chromium sites will align ferromagnetically, and then there will be ferromagnetic interlayer coupling across the van-der-Waals gap, resulting in an overall out-of-plane anisotropy. Chromium trichloride is a little different. So here the moments still align ferromagnetically within each layer, but this time there's an in-plane, easy plane anisotropy. And moreover, there's an anti-ferromagnetic interlayer coupling across the van der Waals gap, leading to an overall cancellation of the moment in the bulk crystals. So in our lab, what we like to do is study what happens to these materials as we take them down to the ultrathin limit. So we begin with bulk crystal growth of our crystals in our lab using chemical vapor transport. We are then able to use mechanical exfoliation to obtain very thin crystals and then assemble them into devices which we can measure in a variety of ways. So first I'm going to focus on our results on chromium triiodide. So if we look at the bulk crystals that we grow, we can already really see this platelet-like shape. And if we zoom in along the edge using SEM, as we zoom in further and further, we could really see the layered nature reveal itself. So as you go down to a higher magnification, it really looks like the pages on the side of a book coming apart from one another, which is a strong indication among bulk crystals that this should be able to be exfoliated. So indeed, we can mechanically exfoliate these onto silicon oxide substrates, just as is done with graphene, boron nitride, and other van der Waals materials. However, unlike graphene, after just a few minutes in air, these crystals will rapidly hydrate and absorb water and eventually dissolve away. So we've had to invest a lot of effort in the past several years in an argon glove box system in which we're able to take our bulk crystals, exfoliate them, and perform van der Waals assembly all inside the glove box in order to protect our crystals from the degradation. So once inside the glove box, we are able to exfoliate and obtain flakes down to the monolayer limit, which we are able to identify using optical contrast techniques, since we don't have the capabilities of doing AFM or other things outside of the glove box. So now we want to see what does the magnetic order look like in the few layer limit compared to the bulk. So the technique that we first used is called the Magneto-Optical Kerr effect, or MOKE. And I should say this was done in collaboration with Xiaodong Xu's group at the University of Washington. So the way that MOKE works is that you shine linearly polarized light incident to your sample, and then you measure the reflected light. And if there's an out-of-plane magnetization in your thin film, then the linear polarization will be rotated by what's called the Kerr rotation. And so this is a very sensitive probe of the out-of-plane component only, but then if you're able to apply a magnetic field and change its magnetization, then you can track how the Kerr rotation responds to the magnetic field and therefore get a better understanding of the magnetic order. So when we looked at our MOKE signals of monolayer, bilayer, and trilayer chrome iodide, we saw several surprising things. So first of all, we saw that monolayer has quite a robust ferromagnetic hysteresis loop. So this demonstrated to us that monolayer chrome iodide is an icing ferromagnet. So naively, if you were to just take bulk chrome iodide and isolate a single layer, this is what you would expect. So the moments point perpendicular to the sheet. However, when we looked at bilayer chrome iodide, we saw that at zero applied field, there's no Kerr rotation. So there's no net magnetization. And then we only see a finite magnetization once we apply a larger field. And then at trilayer, we return to a non-zero magnetization at zero applied field. So these results were quite puzzling to us at first, since bulk chrome iodide is an out-of-plane ferromagnet. And what we ultimately came to understand is that ultrathin chrome iodide is actually a layered antiferromagnet. So the way that we can understand bilayer chromidide is that each layer still has this ferromagnetic ordering within the layer, but now there's a transition from a ferromagnetic to anti-ferromagnetic interlayer coupling, which results in this net cancellation at zero applied field. And then once you apply a large enough field, you'll polarize the layers in both states to be aligned with the out of plane field. So because of this very discrete jump, this poses an opportunity of, can we actually electrically control this magnetic transition? So the ultimate goal for an application in this manner would be to have some sort of current or voltage control to be able to act as a switch. And so you'd want to be able to reversibly drive between the AFM and FM states, which for, say, magnetic memory, you would think of as a 0 or a 1 state. So in order to carry this out, we fabricated these gated bilayer chrome iodide devices, again, in collaboration with Xiaodong Xu's group. And so we use hexagonal boron nitride as dielectric layers and use a graphite top gate and silicon global back gate. And so here's an optical microscope image of our stack. And so first, what we see, if we look at the Kerr rotation as a function of both the applied field and the gate voltage, is that we're able to linearly tune the spin flip transition field with the gate voltage. So if we look at the horizontal line cuts in this mega sweep, we can see that we're able to tune the coercive field or the spin flip transition by about plus or minus 0.2 Tesla just by applying the gate voltage. However, what's more interesting is if you instead look at the vertical line cuts. So suppose that you fix the magnetic field at a constant value near the spin flip transition and now only change the gate voltage. What we're able to do in this manner is actually achieve the gate control of the AFM-FM transition in bilayer chromidide. So at fixed but finite magnetic fields, we're able to reversibly drive between this AFM ground state and the ferromagnetic state using only the gate voltage. So this was a very important step for us in being able to demonstrate that 2D magnets could be used for electrical memory devices by achieving electrical control. However, we still relied on an optical readout, and ideally we would like to also have an electrical readout system for 2D magnets. And so one approach that we thought of is that since chromium triiodide is an insulating magnet, could we perhaps tunnel electrons through in order to figure out the magnetic state? So first, I'd like to explain just what happens when you have transport between across several magnets. So if you imagine this stack where you have two ferromagnets separated by a non-magnetic spacer, and in one layer the magnetization is fixed and the other one we're able to change it, then it turns out that the resistance will depend on the magnetization between the two ferromagnetic layers. So when they're aligned, you'll have a low resistance, and when they're anti-aligned, you'll have a high resistance. And so this is called giant magnetoresistance, or GMR, and this was actually awarded the 2007 Nobel Prize in Physics and is widely used in a variety of applications today. So most notably, if you have a hard disk drive, the read head actually relies on a GMR-based readout in order to locate on the disk drive whether it's in a 0 or 1 state based on the read current, whether it's a high or low resistance. So the GMR type device generally relies on ferromagnetic metals, but in our case, since we have a magnetic insulator, instead we want to look at the spin filter magnetic tunnel junction. And here the same principle still applies, where the tunneling resistance will depend on the magnetization in your stack. And so the underlying principle behind spin filter magnetic tunnel junctions is called the spin filter effect. So if you first imagine having a paramagnet and you send in a non-spin polarized current, so equal population of spin up and down electrons, then they'll both face the same barrier height and have an equal probability of tunneling across. However, if you now cool below the Curie temperature, you'll end up in a ferromagnetic state where now actually the density of states is spin dependent. And so in this simple example, if you send in a non-spin polarized current on the left, the spin up electrons will experience a much lower tunnel barrier than the spin down electrons, and due to the exponential sensitivity of the tunneling probability on this barrier height, you'll end up with far more spin up electrons than spin down electrons tunneling across, and you'll end up with a spin polarized current. You can then take advantage of the spin filter effect further in what is called a double spin filter, in which you have multiple magnets within your tunnel barrier. And here the resistance, just as in the GMR case, will depend on the relative magnetization of the two magnetic layers. And so again, we'll have this low resistance when they're aligned and high resistance when they're anti-aligned. And this work was really experimentally pioneered by Jagadish Mudera's group, also at MIT, using europium sulfide layers. And they're indeed able to demonstrate a switching between a high and low resistance state by applying a magnetic field to selectively switch each of the two layers. So we wanted to then take this double spin filter into the van-der-Waals world. So we made use of graphite as the non-magnetic electrode and can fabricate these van-der-Waals heterostructures where we can actually think of bilayer chromidide itself as acting as a double spin filter due to the decoupling of the two layers by the van-der-Waals gap. So ideally, we'd like to be able to tunnel through chromidide to electrically read out its magnetic state, so whether it's in the anti-ferromagnetic or ferromagnetic state. So we carried out this device assembly inside our glove box, where we used hexagonal boron nitride on top and bottom to protect our tunnel junctions. And we aligned the two graphite contacts such that the only overlap area was through a chromium triiodide barrier. So in order for electrons to go from one graphite layer to the other, they'll have to vertically tunnel through this junction. So if we first look at the zero bias conductance as a function of magnetic field in bilayer chromidide, we see this very discrete step as we go from zero to finite magnetic field. And what this is the direct electrical detection of the AFM-FM transition in this material. And if we sweep in the opposite direction, we'll see similar results. So it turns out that we actually have quite a large magnetoresistance, even at zero bias conductance in these devices. And we can estimate that there's a rather large spin polarization in this double spin filter. So then if you actually add more layers and go to a 4-layer case, we find not only an even larger magnetoresistance, but that we can also estimate that the spin polarization is approaching unity. And so these sorts of devices could be a potential source of spin polarized current that could be of interest to the spintronics community. So now I'd like to return to this nagging question throughout my talk, which is why is ultrathin chromidide anti-ferromagnetic if the bulk is ferromagnetic? So we're able to take advantage of this fact, but ultimately, why is this happening? And what does it mean about the other chromium trihalides? So in order to try to answer both of these questions, we decided to then grow chromium trichloride, a sister compound, which is analogous in crystal structure to chromidide, but in the bulk already has in-plane magnetic moments and anti-ferromagnetic interlayer coupling.
Sorry, Dahlia.
Yeah.
Leon has raised his hand to ask a question, I presume.
Yeah, that's right. Can I ask a question about it was a couple slides ago where you were talking about the spin polarization? Yeah, here and in the previous one. So does one really, for these localized moments, I have a hard time understanding what a imperfect spin polarization is in a ferromagnet. I mean, could this, not suppression to zero, just be, for example, co-tunneling, something like that, which can happen?
Yeah, so this is definitely...
does it really, do you know that this actually reflects the polarization?
Yeah, so these are just estimates based off of just taking like simple math from the high and low conductances. So this is not the actual measured spin polarization, which would require a spin sensitive sensor on the other side. So we don't actually know the degree of spin polarization in these devices.
And even what it means? I mean, what does it mean exactly for a localized moment system, the spin polarization? I mean, one can talk about the moment, the percent of the local moment, uniform magnetization.
So we definitely do still see quite a big difference between when they're in the anti-ferromagnetic versus ferromagnetic state. So it is consistent with this double spin filter
Yeah,
idea.
That makes sense to me. I'm just not even sure what the physical interpretation is when you say estimated spin polarization, what it really means.
So I guess
thought
we're
the formula
trying.
has something to do with polarization of electron bands, kind of a population of
No.
majority and minority spin occupation of bands.
It's more of looking at if it's in the high conductance state, then we're assuming that it's mostly spin up. Whereas if it's in the low, then it's a mix of both. So in our paper, we do define where we get this G plus and G, or G up and G down, but it is related just to, it is a very naive picture, just looking at the high and low conductances.
I think, sorry, this is Bevan. I think if you had a system which was not fully spin polarized up or down, for instance, if your anisotropy were not as large as assumed, then the tunneling, I mean, you wouldn't expect 100% spin polarized tunneling, correct? If your spin were, say, canted slightly out of, away from fully spin up or fully spin down.
If it were canted.
Or canted.
Why would it be canted?
I'm not saying that it's, I mean, the anisotropy surely is large in chromium trihalides.
Well, canting would mean a difference in symmetry, or maybe there's a DM coupling between the layers or something, or it actually prefer to be in plane.
So I guess in this case, since we're also applying quite a large out-of-plane field, I don't think we would expect any in-plane contribution, though definitely it is a very naive picture to say there's only up and down spin polarization of electrons tunneling, because there is still components in all other directions that can tunnel through, though it is favored to be along this spin polarization direction of the material.
Maybe we can go on. I don't have any more. No, maybe there are a bunch of chat messages.
So in chromium trichloride,
I had a question.
Here, maybe we can ask a second question by Ramachandra Bangari.
Yeah, my question was, this particular slide. Yeah, so here we have ferromagnetic and antiferromagnetic states. So, like, we also need to know how long they're going to stay, right? If you want to use it for some application. Do we have any idea about once you? So we also applied gate voltage to change it, right? To get antiferromagnetic and ferromagnetic. So, like, how long is it going to stay once you remove the gate voltage applied?
I believe that if you remove the gate voltage, I think that I cannot remember if it does change. Certainly if you remove the field.
To act as a memory device, you set it at a particular state, right? And then you come back and then read it after that. So it should stay for a while, I guess.
Yes. So ideally you would want to not have to keep a fixed voltage on it to be able to flip it. So I guess a different approach could be to take advantage of these two nearly degenerate states as well, because you can also polarize selectively into one of these two states. So there are different possibilities for making a memory bit out of these bilayer chromidide states.
Okay.
So in chromium trichloride, it's a layered antiferromagnet in the bulk, And so it's well understood to have a bulk magnetization that will saturate with an in-plane field in an arbitrary direction within the plane of about 0.2 to 0.25 Tesla. So given that chrome iodide displayed different magnetic behavior in the few layer limit compared to the bulk, we wanted to ask the question, will this magnetic behavior persist in the few layer limit of chrome chloride as well? So we decided to fabricate these magnetic tunnel junctions quite similar to chrome iodide, where we have the two graphene contacts with the overlap through the chrome chloride layer, and again, use hexagonal boron nitride to encapsulate our devices, except this time we're going to apply an in-plane magnetic field in order to study the antiferromagnetic coupling between the layers of chrome chloride. So just to walk you through our experiments, what we expect to see is that in bilayer chrome chloride, we start out in the antiferromagnetic ground state. So in the double spin filter picture, we have this high resistance state. Now, as we apply an in-plane magnetic field, the spins in both layers will begin to cant towards that field direction. And then once we reach an in-plane field of what's called the saturation field, the spins will be fully aligned with that layer. And so now we'll be in the low resistance state. And so we should be able to identify the saturation field by a kink in the magnetoresistance. And then we can use a saturation field to extract the interlayer exchange, because the larger the antiferromagnetic interlayer exchange, the larger the saturation field, because it's harder to polarize these spins in the same direction. So if we look at our magnetoresistance for 2, 3, and 4 layer magnetic tunnel junction devices, we can see that we can achieve quite large magnetoresistances. And just to normalize to guide the eye, you can really see these plateaus in the magnetoresistances from which we can then just read out the saturation fields as a function of layer thickness. And before we even extract the interlayer exchange, we can already see that it is quite different from the bulk. So the bulk saturation field should be all the way down here. So if we use some models, we can then extract the interlayer exchange value from the saturation field, which will depend on the layer number. And what we see is that the interlayer exchange value itself is quite consistent across our 3 device thicknesses. And more importantly, is over a factor of 10 greater than the bulk. And so what we see is this very large increase in interlayer exchange in the thin limit. So just to summarize what we've seen so far, bulk chrome chloride has a small AFM coupling, which increases by a factor of 10 in the few layer limit. Bulk chrome iodide is a ferromagnet, whereas few layer switches to antiferromagnetic coupling. So these results have been quite puzzling to the community and have gathered a lot of attention on the archive by theorists trying to figure out what's going on. And the dominant word that seems to pop out is stacking. So the hypothesis is that stacking could be playing a role in modifying the interlayer coupling in these magnets. So this one paper looks at first principles calculations in bilayer chrome iodide, where they shift one layer with respect to one another. And what this does is it changes the orbital overlaps and super exchange pathways between the different chromium sites. And what this leads to is a change in the interlayer exchange between ferromagnetic and antiferromagnetic states. So we wanted to see if we could experimentally verify whether this stacking order is indeed playing a role in the chromium trihalides. And we were focusing on chromium trichloride. So we found that in the Raman spectrum of chromium chloride, there's a peak at 247 wave numbers that's quite strong in the Raman spectrum that's actually very sensitive to the stacking transition. So it's been published that at 240 Kelvin, right at the stacking phase transition, where it goes from the high temperature monoclinic to low temperature rhombohedral stacking, there's a shift in the Raman peak by about 2 wave numbers. So we went ahead and looked at our bulk crystals and confirmed that right at this temperature, we indeed see a shift by 2 wave numbers. However, in our thin exfoliated flakes, we saw no shift in the peak, not only at 240 Kelvin, but even down to 10 Kelvin below the nail temperature of the material. So we see that there's no evidence of this stacking transition from monoclinic to rhombohedral as we cool our exfoliated flakes, unlike the bulk crystals. So this leads to the question, does that mean that the thin chrome chloride is for some reason remaining in the monoclinic phase, even down to low temperatures? So in order to study this, we can look at the symmetry of this peak that we've been studying. So it turns out that it's actually a set of two different Raman modes. So in the rhombohedral phase, it's a set of degenerate phonon modes. So if you change the Raman polarization angle, you'll favor one mode over the other and change their relative intensity. But since they're degenerate, you'll see no actual change in the energy of the peak that you observe. However, in the monoclinic phase, at high temperatures, these phonon modes are actually split slightly in energy. And so as you change the Raman polarization angle, you'll actually change the overall peak energy that you observe. And from the Raman tensors, you can work out that you expect to see a fourfold peak energy oscillation as you sweep the polarization angle from 0 to 360 degrees. And so indeed, in our bulk crystals, we see that the peak energy shifts in this fourfold pattern at room temperature, consistent with the monoclinic stacking. And as we cool below the phase transition, we see that this is strongly suppressed. However, in our exfoliated flakes, we see that it's quite strong at room temperature, but also persists down to low temperatures. And we do also see this down to 10 Kelvin below the nail temperature. So therefore, on the basis of temperature and polarization dependent Raman, we conclude that while bulk chrome chloride undergoes this monoclinic to rhombohedral stacking phase transition at 240 Kelvin, it appears that ultrathin chrome chloride remains pinned in this monoclinic stacking at all temperatures, even below its magnetic transition. We then collaborated with Tim Kaxiris' group at Harvard for DFT calculations to perform a similar calculation on bilayer chrome chloride. And what they find is that if you fix the layer spacing, you'll see a larger energy difference between the FM and AFM states as a proxy for the antiferromagnetic exchange in the monoclinic stacking than rhombohedral.
Dahlia, you have roughly 5 minutes left.
Okay, thank you. And so this supports the larger AFM exchange for the monoclinic phase, consistent with our experimental results. So there's been further stacking evidence since our publication on chrome chloride, also in chrome iodide. So this one paper looks at second harmonic generation of bilayer chrome iodide, and what they find is that their spectra are consistent with the monoclinic symmetry and also rules out the rhombohedral symmetry, which would require a C3 symmetry axis. And so these were performed at low temperature. There's also been a very interesting study of scanning NV magnetometry of thin flakes of chrome iodide, and they actually accidentally punctured a region of a 9-layer flake with their tip, but they were able to measure both before and after the puncture. And what they found was a shift in the Raman signal, as well as a large increase in the magnetization from by a factor of 9, which is consistent with an AFM to FM transition by relaxing the flake locally due to this puncture. There's also been some quite recent results looking at magnetic force microscopy of thicker flakes of chrome iodide. And what they argue is that in all of their crystals, they see that the outer surface layers seem to adopt this layered antiferromagnetic structure, about 12 nanometers thick in either direction, but then the inner layers are ferromagnetic and in the rhombohedral phase. So in a bulk crystal, you would expect to see these inner layers dominate compared to the 25 nanometers or so outside, but as you thin down the crystals, then you only end up with the surface layers, which remain pinned in the monoclinic stacking. So this is a very important clue in perhaps where this transition starts to happen as you look at perhaps thicker flakes of chrome iodide. So to summarize, the chromium trihalides are an exciting new class of 2D magnetic insulators, where we have ultrathin chrome iodide, which is a layered antiferromagnet, and in which we've been able to demonstrate at least the possibility of electrical control and readout of 2D magnetic states as a towards applications perhaps in other van-der-Waals magnets. We've also used ultrathin chrome chloride to teach us the important lesson that stacking and magnetic orders are quite strongly linked in these materials and are an important factor to keep in mind as we thin down bulk crystals of other 2D magnets as well. So moving forward, now that we understand both what the behavior is in the few layer limit and why it may differ from the bulk, we can begin to assemble van-der-Waals heterostructures incorporating 2D magnets. So this one early work looked at monolayer tungsten diselenide on top of a thick layer of chromium triiodide, and they were able to see valley splitting due to the underlying chromium iodide magnetism. There's also opportunities to continue to explore the van-der-Waals spintronic side using these magnetic tunnel junctions and perhaps actually confirm these spin polarized currents that we believe we are generating. And just last year, there was this nice result from Qinfei Mak and Jishan's group demonstrating a bilayer chromidide spin transistor in which they were able to combine both the electrical switching and readout in a single device. And finally, now that we've developed techniques for fabricating devices in an inert environment, there's a whole host of different van-der-Waals magnets that have been studied in the bulk, sometimes decades ago, but we can now reintroduce in the thin limit. And they include more exotic magnetic textures than just ferromagnets and antiferromagnets. So of course, there's the KITP quantum spin liquid state that we heard about in the previous talk. And there are also other opportunities to explore, including magnon interactions. So these honeycomb ferromagnets have Dirac magnon spectra, kind of an analogy to the Dirac fermions in graphene. So there's certainly a lot of interesting physics as we take magnets down to the ultra-thin limit. So I'd like to thank the many people who have been involved in these projects over the years. In particular, I'd like to thank my advisor, Professor Pablo Herrero at MIT, and the two postdocs who I've worked with over the course of my PhD, as well as Xiaodong Xu and his group at the University of Washington for our many collaborations. I'd like to thank all of you for listening to my talk, and I'm happy to answer more questions.
Yeah, thanks for the nice talk. Interesting. So we do indeed have questions. Yaroslav Blanta has raised his hand.
Thanks for the great talk. I have a question about the detail probably, but you mentioned, I think in both chromium iodide and chromium chloride, that you have 2 to 4 layers.
Mm-hmm.
Now, do you just assume that electrons don't tunnel through the pieces when there are 4 layers and they only tunnel through the 2 layers?
No, so we still are assuming that they're tunneling through all the 4 layers.
Then why don't they screw up everything if they tunnel through 3 and 4 layers? So
in the case of both thin chrom iodide and chrom chloride, we think of it as a layered antiferromagnetic state. So we are still thinking of it, in the case of trilayer, we are thinking of it as an up, down, up.
Okay.
Yeah.
Jeff Rao has raised his hand.
Hi, just a quick question about the direction of the inflame moment. Is it the same for the thin films as it is for the bulk?
For chrom chloride? Yeah, so it is an easy plane anisotropy. So we weren't able to take measurements with a vector magnet, but other groups have, and they don't detect any anisotropy within the plane, within the XY plane. And so that seems to be consistent in both bulk crystals as well as the thin crystals.
So is there in the bulk, there's a preferred direction though, right? For in the plane, or is it just very soft, or has that been measured?
I believe it's just quite soft. There might be a slight preference, but I don't think, not that we were able to resolve in our experiments or
okay.
That's important.
And the films look similar?
Yeah.
Okay, thanks.
Next up, we have Oleg Stark.
Hi. So wanted to ask about temperature dependence of magnetoresistance data, at which temperature were experiments taken, and and then how it depends on temperature, if it does.
Yeah, so I didn't include the temperature dependence in the interest of time, but it is published. So all of the measurements were generally done at 4 Kelvin, well below the Curie and Néel temperatures. So you do see that it is less sharp as you approach the Curie or Néel temperature. And then for some of the chromidide results, we also took it 300 millikelvin in a helium-3 refrigerator. We did see that the features were slightly sharper, but the overall behavior was no different than at 4 Kelvin.
Okay, and what is the Curie temperature?
So in chrome iodide, it's 61 Kelvin for the bulk, and it goes down to about 45 Kelvin in the monolayer.
Okay.
But once you go to bilayer, it's a little bit higher. And then in chromium trichloride, it's between about 14 and 18 Kelvin.
Okay, and so just so that and you observe magnetoresistance remaining at whatever percentage that you find. I mean, roughly, as you heat up to the transition, magnetic transition temperature. It
does start to decrease, though below a certain temperature, you stop seeing an increase. So all the measurements were taken once it had already plateaued at the maximal value.
Okay, thanks.
Mm-hmm.
Next up, we have Rosa.
Yes, I have a question on this fact that you mentioned this ferro-antiferromagnetic interlayer is very much related to the stacking, whether you have monoclinic or rhombohedral. So my question is, because you also go to this monolayer, 2 layers, 3 layers, how much can you then control, in fact, this type of phase transition? Because if I think about a monolayer stacking or a rhombohedral, the rhombohedral, I have some small twisting with respect to the monoclinic case. So can you control that in the same way as it is being done with twisted graphene bilayers?
Yeah, so that's a good question. So we haven't, so there, in principle, you can twist and then perhaps favor in different regions of the moire, within the moire unit cell, you may be able to favor different stacking configurations. And also the stacking order can be controlled by pressure. So we have not done this, but other groups have explored in magnetic tunnel junctions with chromium triiodide. By applying pressure, they are able to irreversibly go from the anti-ferromagnetic to ferromagnetic phase, which they attribute to stacking changes by applying pressure.
Oh, very interesting. Thank you.
Okay, are there any further questions? So that doesn't seem to be the case. So let's thank Dahlia again.